When you know the natural variation in a process, setting the control limits is actually simply an issue of selecting the appropriate z-value. This particular scenario, we do know the natural variation in the process. It isn't actually stated on this particular note sheet. It's relying on us remembering scenario 1. But nonetheless, I do. Let's look. The main house gaming production manager needs a mean chart to monitor the production of 20 millimeter round tiles discussed earlier in scenario 1. Oh, and this is what I mean. In that scenario, the machine that cuts the tiles that's packed in the board games can cut them with an average diameter of 20 millimeters. And this was the important issue, a standard deviation of 0.1 millimeters. Now, before we go any further, refresh our memory. Wait a minute, what did that mean? The machine cuts 20 millimeter tiles. They do if you measure them finely enough. Vary a tiny little bit. That's the natural variation. Oh, and it's expressed as a standard deviation of 0.1 millimeters. You say, yeah, okay, I got that. Okay, fine. Now, what's new with this particular scenario? The machine operator will measure 4 round tiles at random every hour. Ooh, this is important. Measure 4 round tiles and plot the average of the 4 diameters on a mean chart. We definitely want to record this new information because what was described to us was the sample size. We're being commissioned here to set up a mean chart that the machine operator for the tile cutting machine can use in the future. The machine operator is going to, in the future, pull 4 tiles at random. That's the size of the sample. We need that parameter in advance to set up the chart. Okay, we found it. Now, what is it that we're actually being asked to do? What would this mean chart look like if the production manager wishes 99.7% of all 4 tile samples to fall within its limit, given that the machine is in control? The manager has just provided us the last reading that we need, in that the manager has just told us the degree of producer's risk that Main House Gaming is willing to tolerate. Oh, wait, you say, huh? Now, you can see actually on this note frame, to set up a control chart, you need to find the upper control limit, the lower control limit. We've actually got a blank one here ready to go, and we actually have the center. The center of the road here is 20 millimeters. The question is, upper control limit, lower control limit. How will they be using this? They'll be marking sample average diameters in the future. If they fall out here, they were too wide. If they fall in here, the average diameter was too narrow. And in either case, that would signal that there was something wrong, and then they would stop the machine and they would look for the problem. Right, that's the purpose of the control chart. Now, wait a minute, what did I mean by the producer's risk? Because it looks like we just will need to fill in those formulas. Yes, we do. Notice we have everything but not quite that we need to fill out the formulas. We had better think about the statement that was made. Here's the idea. We believe that natural variation in tile cutting is normally distributed. So I am trying to draw a normal distribution, except up on its side, to represent it naturally wobbling around this center of 20 millimeters. Now, what I drew here, right there, isn't actually the distribution that describes the natural variation. That's the distribution that describes the natural variation in the samples. How's that any different from the natural variation in the individual tiles? Oh, we expect that the natural variation in the samples will be somewhat less crazy than in the individual tiles. Oh, but at any rate, what the manager said was that when in fact there is nothing wrong with the machine, it is cutting tiles naturally. The manager wants to see 99.7% of the samples naturally fall within those limits. Meaning that, let's see, that doesn't leave a whole lot left over. 0.3% of a chance, producer's risk. We did amputate a tiny little bit of this natural sampling distribution by setting these hard limits. Their combined area is known as producer's risk. Because if in fact nothing's wrong, what this is indicating is that there is a 0.3% chance, a tiny chance, but nonetheless a chance, that a sample will be pulled, 4 tiles will be measured. That sample, the average reading, will either be declared too wide or too narrow. It will fall or chart outside those limits, and we will say, oh, something's wrong, when in fact nothing's wrong. That was just a really freaky sample. Sometimes that happens because of the natural variation. That's why it's called producer's risk, because it's the risk of accidentally stopping production and looking for, tearing down the machine, a problem that isn't actually there. Oh, all right, anyway, so we have to set these limits. This is the last reading that we need to set the limits. We have to set these limits such that we meet this expectation. And there actually is a really fast answer to this. I wonder why it was 99.7%. They wanted 99.7% of the samples to fall within the limits, when in fact the process is in control. Goes back to the normal distribution. Oh, because natural variation is normally distributed, the distribution of the samples is also expected to be, the natural distribution of it, normally distributed. 99.7%. If you want to capture 99.7% of a normal distribution, any normal distribution, it doesn't have to be for a control chart, it doesn't have to be for main house gaming, any normal distribution, 99.7% of its bulk, what I shaded in yellow, will be within 3 standard deviations of the mean, or its center point. Okay, that's a defining characteristic of the normal distribution. You say, huh? They happen to be asking for 99.7%. Rule of thumb, that is 3 standard deviations from mean. And you say, yeah, okay, but I'm looking at these formulas over here and I'm not seeing where you put in the number of standard deviations from the mean. Actually, it's right here. It's the one thing, the one number we hadn't quoted yet. Yeah, because to set these limits, the only thing we need to do is fill out these formulas. We have mu, that's 20. We have sigma, the standard deviation in the natural process, that's the 0.1. This was both, when we started this in scenario 1. And that's why I said it was really important to spot the size of the sample, because you can see it being used here, because this whole portion, oh, by the way, of the formula is the standard deviation in the sample means. This is the standard deviation in the whole process, how much the individual tiles vary naturally. This is how much the samples of 4 vary when you compare their average diameters. Oh, well, anyway, I think that's about all the detail we can add to this, because once you realize that what they happen to be asking for fits the rule of thumb of 3 standard deviations from the mean, that's what Z is. Z is literally the number of standard deviations of the sampling process that's going to be, to the top and to the bottom, which is from the mean. Oh, which means to finish this question, the only thing we have to do now is fill out that formula, and now we have all the pieces. Because for the upper control limit, you would say, all right, 20 plus 3, because of that statement there, divided by, all right, 0.1, I have to be careful, divided by, times 0.1 divided by the square root of 4, so that's 0.1 divided by 2, so that's actually like 0.05, I think. Anyway, on my calculator, as a finished result, I get 20.15 millimeters. That is the upper control limit here. For the lower control limit, almost the same scratch work, just be careful, it's 20 minus z equals 3 times 0.1 divided by the square root of 4, or I get 19.15 millimeters. Lower control limit. So this is what the mean chart should look like. So did we answer the question? What would the mean chart look like if? Yes, exactly. It would look exactly like that. Now, that mean chart that we just finished was based on the statement that they wanted 99.7% of the samples to fall within the limits when in fact the process is in control. There is a follow-up question in this scenario, almost the same exercise. What is the only thing here that's different? Let's look at this. What would the chart look like if the manager was willing to reduce this requirement to 95.5%? Now, reduce the requirement, meaning, okay, there's less that will be naturally trapped within the limits. It's important to realize that that increases producer's risk. I mean, we didn't need that statement to basically respond to this question, but it's an important point because they're saying, okay, they're willing for those tails to be a little bit larger. Fine. What should the chart look like? Well, it's going to have the exact same center. We're going to use the exact same formulas from last time. No, wait a minute. Might as well draw the image. Don't have to do this to set the limits, but it helps me to see what we're doing. The only thing that we're doing here is we are setting these limits such that we have slightly larger tails, slightly larger producer's risk, because only 95.5% of the samples naturally fall within the limits. Oh, okay, well fine, let's just set the limits. It is upper control limit, the exact same formula. And lower control limit, the exact same formula. And if you think about it, this didn't change. I already went ahead and designated that on the graph. This isn't changing. The sample size isn't changing. Right. Producer's risk is embodied in that one parameter, the z value, the number of standard deviations. Oh, okay. Now, they said this time they're willing for only 95.5% of the samples to naturally fall within the limits when in fact nothing's wrong. What z are we supposed to use? Why 95.5%? This is another very common rule of thumb. Oh, just as I said, one defining characteristic of a normal distribution is 99.7% of its bulk is caught within 3 standard deviations. That was the question before. 95.5% of its bulk is caught within 2 standard deviations. Rule of thumb for 95.5%. Z equals 2. Oh, no wonder they're quoting that particular amount. Oh, all right. Oh, so we just repeat the formulas that we had filled out for the question before, except we use a Z of 2 instead of 3? The answer is yeah. That's exactly what we do. Okay, what would the chart look like? Well, the upper control limit would be 20 plus, now it's 2 times 0.1 divided by the square root of 4. All right. I did that. Where's my scratch work? Oh, I get 20.1 millimeters. That's where we draw the line on average diameters. Down here, 20 minus 2 times 0.1 divided by the square root of 4. Be sure to do that in the brackets first. And I get 19.9 millimeters. There, that is exactly what the chart would look like. Now, interesting. How does it compare to the chart before? Here it was 20.15, 19.15. Here, upper control limit 20.1, lower control limit 19.9. Do you notice that in agreeing to tolerate a little bit more producer's risk, what the manager has done is commissioned a chart that, in the case of the second question, is essentially narrower.